Hello, in this video we're going to continue our exploration of different potential triangle congruence criteria. And we're going to look at the SSS, or side-side-side triangle congruence correspondence, and see if that's enough to make the triangles congruent in Euclidean geometry. So once again, we can control things with the sliders here, or just by typing in some numbers. Like this, say 5, 6, and 8. And how do we work this? Well, first of all, pick a point A, go out the first length of AC, or AB, which we're going to call little c. That's a length of 8. Pick any point on there. So B can be free to move anywhere along here. A is free to move anywhere in the plane. And then complete that side. So now we have 2 of the vertices and 1 of the sides, and it must be length 8. Next, where does the other one have to be? Well, the length from A to C, AC, is going to be length B. That has to be 6. So that has to be somewhere on this circle for that to happen, circle A. And there's also has to be somewhere on circle B of radius 5. And we see that there are 2 places that those circles intersect. So there are 2 possible triangles here. And we can finish out the triangles. So notice those have the correct side lengths, but so do these. So potentially these are not congruent, or are they? Let's see. So when we do the measurements, we find out that sure enough, these actually are congruent, and it doesn't matter what orientation we put this thing in, and it really doesn't matter what size the sides are. Notice that these possible things that we have here always give us triangles that are congruent. Well, or do they always give us triangles? Let's take a look back here. There is a possibility that you can get this, that the side lengths of the blue relative to the red and the green are, blue's too long and the other 2 are too short. So, again, we have our length here for AB. The distance C, which is AC, B, which is AC, is got to be this distance. So the vertex has to be on that red circle, but it also has to be on this green one. If those are too short, then it doesn't meet. Okay, so let's try something here. Let's call this one 4 and this one 8 and say this one 12. Now the circles do meet, but they only meet at one specific point. Okay, those 2 circles are tangent to each other, and they meet at a point between A and B on line segment AB. That's not going to make a triangle when we try to connect up, these pieces. See, that 4 and the 8 adds up to the 12, but it doesn't give you an actual triangle there. So if the 2 things add up to the same, the 2 shorter side lengths add up the same as the longest side length, we get basically a line segment, not a triangle. If this B is, if A is even longer, AB is even longer here, now the 2 circles don't even touch at all, and now once again, no triangle is possible. So this illustrates something that we call the triangle inequality. That is that the sum of, if you actually have a triangle that exists, the sum of the measures of any 2 interior angles has to be greater than the measure of the third one. In particular, if you take the 2 smallest angles with the 2 smallest measures, if you add those 2 measures, they have to be strictly greater. That sum has to be strictly greater than the length of the hypotenuse. That's the length of the longest side. So the SSS condition either results in 0 congruence classes whenever the triangle inequality is not satisfied, when the 2 shorter sides lengths add up to less than the longest side length, or the same. And when the triangle inequality is satisfied, when the 2 lengths of the 2 shortest sides add up to more than, strictly greater than, the length of the longest side, then in fact exactly 1 triangle congruence class exists. All those triangles are the same. So the SSS condition is enough to guarantee that 2 triangles are congruent if they actually two triangles actually exist, and all three pairs of corresponding sides are congruent, then in fact the two triangles must be congruent. Their angles, in other words, must be congruent as well. Next, I want to look at another exploration of this. Let's look here. Is a nice little dynamic exploration. Let's open that in the app. And here we can adjust the lengths of the three sides. Okay. And so we have three sides there. Okay. Now let's see what this does. It's going to, now we have another triangle over here. Potentially that's congruent. Let's see if it is. We notice that that side is the same length, that side's the same length, and that side is the same length. So according to what we've just seen, that should be congruent. Now we should be able to get there via some sort of transformation. One way we can do it is, in this case, we flip that over. Let's see. And slide it over like this. And we can see that those triangles are congruent now by side angle side. And you see those angles are congruent. So we could get there by, let's see, by doing a translation. Well, this one used a reflection, a translation, and another reflection. A translation, a rotation, and another reflection. So we've seen that the side-side-side correspondence criteria is enough to make the two triangles congruent in Euclidean geometry. We'll explore this in some other geometries in the next couple of videos.